All right, let's jump right into this explainer. Today, we're looking at some truly extreme engineering. We're talking about how we keep electric vehicles safe from one of the absolute most critical electrical failures you could possibly imagine. Now, obviously, with modern EV high-voltage systems, we're dealing with just an immense amount of power, right? Managing all that juice safely is absolutely paramount. So we're going to explore the unsung hero of a whole system, the high-voltage contactor. Specifically, we'll see exactly how engineers prevent it from failing in the most dangerous way possible.
To really get the stakes here, I want you to imagine the high-voltage relay as the fortress gate of an EV. This is it. It's the absolute barrier between all that massive energy stored in the battery pack and the rest of the vehicle. So what happens if an emergency surge current causes that gate to permanently melt shut? Well, the vehicle literally loses its ability to isolate high voltage. Boom! The entire thing is suddenly at risk for catastrophic thermal and dynamic runaway, not to mention severe electrical shock hazards and totally uncontrolled power surges. It's basically a nightmare scenario, which is exactly why automotive engineers classify this under the absolute highest safety risk levels.
So here's the engineering roadmap we're following for this explainer. First, the fatal truth of welding. Second, software and hardware co-diagnostics. Third, DFMEA, key design. Fourth, PFMEA, process control. And finally, number 5, DVPNR, extreme validation.
Okay, let's kick things off with Section 1, the fatal truth of welding. Understanding the physics of failure.
So looking closely at the root cause, the actual technical term for this failure is micro-cold welding. Imagine a catastrophic fault happens in the vehicle, say a severe short circuit in the silicon carbide inverter. The relay is suddenly forced into an emergency cutoff, severing hundreds, maybe even thousands of amps of current. Now, the exact moment those metal contacts pull apart, that electrical current desperately tries to keep flowing, literally jumping the physical gap. This creates such intense heat that it actually vaporizes the surrounding air and instantly melts the silver alloy of the contacts. Then, as the arc finally breaks and that liquid metal cools down, the two sides are permanently fused together. We're talking an irreversible physical weld.
But here's the thing. Extreme arcing isn't the only threat we're dealing with. Massive inrush currents are a huge risk too. If the vehicle's pre-charge sequence fails and the main relay slams shut while there's still a huge voltage difference, thousands of amps hit these microscopic bumps on the metal surface. Engineers call them A-spots. And those tiny spots just instantly melt. Then you've got environmental factors. You've got high-frequency vibrations from the motor, we're talking anywhere from 100 to 1,000 hertz, mixing with wild temperature swings. This causes microscopic grinding known as fretting, which just eats away at the protective coatings and totally spikes the electrical resistance. And finally, the internal springs that are actually supposed to pull the contacts apart, they can literally relax and weaken under all that severe thermal stress, meaning they might just not have the muscle to break a weld if one happens.
Moving right along to Section 2, software and hardware co-diagnostics, basically the EV's immune system.
The absolutely crucial point here is continuous surveillance. You see, the vehicle never just assumes the relay is working. It constantly forces it to prove it. At startup, or what we call key on, before it even tries to close those main relays, the system checks the voltage. It should read 0. If it detects high voltage that's sitting within 10 volts of the battery, it instantly knows, hey, a relay melted shut during the last drive, and it immediately halts the startup. Conversely, at key off, the system actively discharges the power. It watches closely to ensure that the voltage drops drastically within just 2 seconds. If that voltage stays pinned high, the system knows the relay is stuck closed, and it flags a critical failure right then and there.
Now, what's genuinely incredible about this is the reaction time. If a welded contact is detected, the vehicle has a vanishingly small window to react. We're talking 60 milliseconds or less. To pull this off, the system relies on an ASIL D dual-core doer checker architecture. It works like this. One processor core, the doer, executes the commands, while a totally independent safety core, the checker, constantly watches its every move. If that safety core sees a welded contact, it bypasses absolutely everything. It completely locks down the vehicle's high-voltage system in under that 60 millisecond window, and it sends a fatal command to the vehicle control unit. That permanent lockout means no future startups are happening until the vehicle is physically repaired.
All right, on to Section 3, DFMEA Key Design, designing to survive the unsurvivable.
I've got to say, this is one of the most fascinating solutions in all of electrical engineering. It's called the magnetic blowout technique. When those contacts separate under a massive load and that deadly plasma arc forms, the relay actually relies on built-in permanent magnets. These magnets apply what's known as the Lorentz force directly to the electrical arc. It literally pushes and stretches the plasma right into a series of cooling grids. And to top it off, this entire violent event is happening inside a hermetically sealed chamber that's pumped full of 90% nitrogen and 10% hydrogen just to suppress ionization. The end result? That highly dangerous metal-melting arc is completely shattered and extinguished in less than 5 milliseconds. Talk about precision.
To further reinforce this gate, engineers aren't just slapping in some standard copper. No way. They are utilizing advanced powder metallurgy, specifically silver tungsten alloys. These alloys possess just phenomenal resistance to high-temperature welding. But they don't stop there. System architects also enforce a dual contactor topology. What that means is they make absolutely sure the positive and negative relays are completely physically independent components. They are never housed in a single integrated unit. So think about it. If one relay suffers a catastrophic weld, the other independent relay can still open. It completely isolates the battery and basically saves the entire vehicle from a single-point failure.
Which brings us to Section 4, PFMEA, Process Control, Manufacturing with Absolute Precision.
Over on the manufacturing side, every single relay that rolls off the assembly line has to undergo a really rigorous two-stage vacuum helium leak test. And the acceptable limit here is incredibly strict. We're talking less than 1 × 10 to the -6 millibars liters per second. So why helium? Well, it's a tiny, tiny molecule, making it perfect for finding microscopic cracks. Enforcing this strict limit guarantees that absolutely zero moisture, or say vaporized transmission fluids, can ever penetrate that sealed arc chamber over the entire lifespan of the vehicle. Because if that inert nitrogen-hydrogen mix we talked about leaks out, or if any moisture gets in, that arc isn't extinguishing in 5 milliseconds. And if that happens, the relay melts. Simple as that.
And right before they leave the line, literally 100% of these units are dynamically tested. They measure the micro-ohm resistance between the contacts, demanding it stays perfectly under 0.5 milliohms. This is crucial to prevent early heat buildup. Furthermore, how the relay actually connects to the vehicle's bus bars is just as critical. The manufacturing process uses automated servo-driven drivers utilizing a torque angle method to fasten phosphate-coated bolts. Doing it this way guarantees the exact axial clamping force required. Seriously, even a slightly loose connection right here could generate enough external resistance heat to melt the entire relay from the outside in.
Finally, let's look at Section 5, DVPNR Extreme Validation. This is the trial by fire.
This validation testing? It's basically a relentless engineering gauntlet. First up, the relays are shaken violently in 3 axes at up to 2,000 hertz, pulling forces of 35 meters per second squared. And they do this while enduring extreme temperature swings for a solid 1,000 hours. Through all of that, any microcuts simply cannot exceed 1 microsecond. Second, they are forced to sever a massive 400 amps at 800 volts, 1,000 separate times. The pass criteria? Absolutely zero welding, and any internal melting has to be kept under 50 micrometers. Finally, they hook it up to a hardware-in-the-loop simulator, and engineers inject a catastrophic fault at 12,000 RPM. The system must hit a fault-tolerant time interval of exactly 60 milliseconds and achieve a 100% PWM block. It's intense.
Honestly, seeing all these complex transient coupling simulations really leaves us with one highly critical, kind of provocative question for anyone looking at EV architecture. Is your pre-charge window tight enough to prevent that fortress gate from melting in the first place? Because think about it, if those voltage thresholds are off by just a little bit, that massive inrush current bypasses all this incredible hardware we just talked about. It's been absolutely fascinating exploring the razor-thin margins of this extreme engineering today. Thanks so much for diving into this explainer with me, and definitely keep questioning how all these complex systems around you really work.